So as you know, yeah, the laser can generate, let's say this is the power versus the frequency or wavelength of the laser. So you can have only, for example, just one line that is emitted at some center frequency and some line width. So this is a single mode laser or a single frequency laser, right? If you see many lines, for example, 3, then we say that this laser is a multi-mode laser, right? Multi-longitudinal mode laser. However, how this is happening that the laser emits many longitudinal modes or just one longitudinal mode. So we can explain it on the example of a helium neon laser, for example. This is a gas laser. I will, of course, describe this laser in more detail on the next lecture, but for now, it's just enough for you to know that this is just a gas laser. It emits light at the wavelength of 32.8 nanometers. That corresponds to the frequency of something like 474 terahertz. So let's assume that our laser has the length of let's say 1 meter. So this will correspond to the free spectral range C over 2L equal to 150 megahertz. Okay, so if we look at the resonances of this resonator, they will look like that. So we have equally spaced resonances. So this was already on the previous lecture, right? And this is the frequency, and this is this might be the transmission of the Fabry-Perot resonator. And as you know, these resonances, they start from 0 and they end they go up to infinity, right? However, we start from 0 hertz, and we know that this mode spacing here equals 150 megahertz, right? 50. So we have 150 megahertz between each resonance, and we can call this resonance a longitudinal mode. So I will say that we have 150 megahertz mode spacing. So as we know, the frequency of this optical radiation is 474 terahertz, and we are now on the megahertz scale, right? So you can say that we will. Oh, this was a bad idea. We can say that we give some break here. So we skip to the terahertz region. So we are now here around 474 terahertz, right? So we are at the mode number million something, right? Because we are far away on this scale from 0. And the gain bandwidth of helium neon medium, especially neon, is centered at this 474 terahertz something around that, and has a width of approximately 1.5 gigahertz. So the gain of helium neon has the width of 1.5 gigahertz. This is the bandwidth of the gain bandwidth, and the center is, let's say, around 632.8 nanometers. So plot this gain bandwidth. So it has a Lorentzian shape. It looks like that. So we have the center here, which is 474 point something terahertz. I don't know the exact number, but this is known up to the, I don't know, maybe 12 or even 15 digit. And the width here is around 1.5 gigahertz. So if the mode spacing of the laser, so the FSR here, is at the level of, let's say, 150 megahertz, then it will happen that there will be many modes under the gain curve. So since the gain is broad enough to support emission of many longitudinal modes, the spectrum of the laser, if we look at the spectrum of the laser that will be emitted in this situation, so this is the power of the laser, it will look like that. So I would have this mode, this mode, this mode, and this mode, and maybe a little part of this mode here. And this will be under this envelope of this gain bandwidth, right? You will see it also on the exercise. So maybe some of you already had the exercise with the helium neon laser on the laboratory. So you can measure the shape of this gain curve. So in this situation, you will have a multi-mode operation. Of the laser, so multi-longitudinal mode, right? Because these lines here are longitudinal modes. So the spectrum of the laser will be the one that I plotted with red lines. These lines will be, of course, very narrow. So they can be really narrow, like, I don't know, maybe kilohertz or even hertz width of these lines, but they will be on this under this envelope of the gain bandwidth of the helium neon medium. So this is a multimode laser. So in every case, when we have a free spectral range of the resonator much smaller than the gain bandwidth of our medium, and we don't apply any other filtering effects, we will always have this kind of multi-mode operation. Of course, there are some issues like competition between the modes and so on. So sometimes some of the modes might be pronounced and some will be suppressed, but in the general case, we can expect a multi-mode operation. But in most of the cases, like because of some metrological applications or in general, very often we would need to have just a single longitudinal mode. So how can we do that? So you can guess that probably the easiest solution would be to design such a resonator to have a very large free spectral range. So let's say these are the modes. So in case of a helium neon laser, let's assume that they are spaced by 800 megahertz. So if we make a resonator, a shorter resonator, because this is C over 2L, so when we minimize L, then we can get 800 megahertz of spacing. We would need to calculate that, but this would correspond to some few tens of centimeters. Then it can happen that the width of the helium neon gain curve, if this is 1.5 gigahertz, it will be not broad enough to cover two longitudinal modes. So then the emission, the spectrum will only, the output spectrum will be only this one longitudinal mode, this one frequency. And then we will have a single frequency laser or a single longitudinal mode laser. Of course, it might happen that L, the length of the laser, will change because of thermal expansion of the material or some other disturbances. And it might happen that these modes will just move around because if we change the L, we will change this free spectral range. So we will change this this spacing between the two modes. So it might happen that this mode will move here into this direction, and then we will excite this mode. So we will see emission from this line. However, if we stabilize the laser, we can have a single longitudinal mode operation. So I hope this is clear.
Yes, it seems to be.
Okay. If this requires any additional explanation, then just interrupt me and let me know. Okay, so let's go next. So, but don't confuse it with the single and multi-mode transverse mode operation, right? So it is good to remember that these transverse modes are related to these TEM X, Y distributions. So we have the TEM00, right? So this was the fundamental mode, or the TEM10, or we can have these kind of distributions like TEM11 and so on. So these are transverse modes. Transverse modes. So longitudinal modes refer to the frequencies that are emitted by the laser, and you can guess that we can have many longitudinal modes emitted as a one single transverse mode. So it can happen that the laser has, let's say, 3, 4, 7 longitudinal modes, and they are emitted from the laser as a single transverse mode. So this is completely fine. And this is not a problem. So please be familiar with the definitions of single multi-mode laser and transverse modes and longitudinal modes. So now we switch to also some basics on the stability of the resonator. So there exists some criteria how to define if the resonator is stable or unstable. So stable means that the waves, or just let's say the photons that are inside the resonator, they will not exit the resonator at any point. So it means that they are trapped inside this resonator, and the beams are just bouncing from one mirror to another one. An unstable resonator means that after some passes of the resonator, let's say after sometimes 100 or maybe millions of bounces between these mirrors, the ray will start to exit from the resonator. And of course, this is in most of the cases something which is unwanted, because we would like to have stable resonator most of the time, but there exist lasers based on unstable resonators, and this is also working. So if the resonator has if the laser medium has enough gain, it might happen that someone wants to have an unstable resonator, and then this beam just acts as an output beam from the laser. So we don't have any transmission from these mirrors, but we have only transmission from so outside this aperture of the mirror. And there exists some criteria, some conditions when the laser resonator is stable or not. And we define two stability parameters of this kind of spherical resonators. So L is the length of the resonators, the spacing between the mirrors, and R1, R2 are the radius of curvature. So this is the radius of curvature of the mirrors. So to make the laser stable, it has to meet this condition. Okay. So if we choose the length of our laser and we choose the radius of curvature, we can just easily calculate this and see if this is less than 1 and more than 0. And if yes, then this is stable. This can be plotted as a stability diagram. And we can define this stability area here filled with these with red lines. This is the area where the laser is stable. So we can, maybe this is better visible. We can also these points for the green points represent different types of resonators. Where are they placed on this stability diagram? So generally, as you can see, some of them are on the edge of the stability region. For example, this is the plane parallel resonator, where the mirrors are flat. They have an infinitive radius of curvature, so they are flat. So you can imagine that if you place two flat mirrors in front of each other, then it might happen that if you slightly detune the angle of this this laser, it might happen that you will jump out of the stability range, or if just by accident one of these mirrors will not have infinitive radius of curvature, will not be flat. The confocal resonator is placed here in exactly in the middle. So this is just an illustration that you need to know that resonators are divided into stable or unstable, and typical resonators like confocal or even plane parallel or this kind of like concave convex, which are used in semiconductor lasers, they are in most of the cases stable. However, in some cases we need an unstable resonator. Of course, there exist many other types of laser resonators, depending on the need and the application, and generally what we expect from the laser. So we can increase the number of mirrors used in the resonator. So the simplest approach is, of course, the two-mirror cavity. So this is an example of the confocal cavity. So the gain medium here, marked as blue here, is usually placed in the radius, right, of the beams here, in the waist of the beam, where it has the smallest radius, so in the focal point of the cavity, because we usually want to have the highest intensity of the beam in the gain medium. In case of micro lasers, so lasers based on crystals, we can directly bond the mirrors on the surface of the crystal, or you can just deposit them using some deposition technology, where we can just coat the mirror with dielectric coatings or silver or metal coatings to make the reflectors. So then we have this kind of bulk crystal, and these surfaces, the front surface and the back surface, can just be covered by the mirror material, and then the resonator is just directly bonded on the bonded to the crystal, right? So we have a micro laser which has a flat parallel resonator. In semiconductor lasers, very often we use an external mirror, which is called VEXEL, which is vertical external cavity surface emitting laser. So the semiconductor, which is here, emits the light, like, let's say, perpendicular to the surface of the semiconductor, and we have a second mirror here that is the output mirror, so the light is propagating here up. But if we need to have some more functionality of our resonators, so for example, we need more than one focal point in our cavity, more than one waist of the beam, then we need to arrange lasers with more mirrors. So for example, 4 cavity mirror gives us the possibility to have 2 waists of the laser beam inside the resonator. So this is an example here, the first one, where we have the waist here for the gain medium, but we can have another waist, for example, for placing some functional components like some dispersion compensation or non-linear materials for obtaining some particular effects. If we will have enough time during this semester, we can also discuss this kind of arrangements where we have some non-linear effects inside this laser. So this is called the bow tie cavity, or a modification Z-shaped cavity, where the focal point is on the back mirror. So we can put something here, and we just increase the, let's say, the flexibility of our cavity. But of course, it is enough to have 2 mirrors to build a laser. A confocal cavity requires 2 mirrors, but if we want to increase the capabilities of our laser, and we just need to have like more focal points, then we can add additional mirrors, curved mirrors, of course. So this is an example of a bow tie cavity that was developed here at our university, and in this case you can see that we have many mirrors, 3, 4, 5, 6, 7, 8, and 9. This is not because my colleague was unhappy having 2 mirrors and he wanted to align 9 mirrors instead of just 2. But this is because each mirror has some functionality. So these flat mirrors can be mirrors that introduce dispersion, controlled dispersion. Dispersion is the effect responsible for broadening or shortening of laser pulses. So this laser emits pulses, very short pulses, and these mirrors have the possibility of shortening the pulse a little bit. And here the last mirror is the CSAM. This is a semiconductor subparabole absorber mirror, which is just a modulator that is responsible for making the pulses. I will also mention about that. But it requires very high intensity, so the CSAM needs to be placed in the point where we have a focal spot. We have the smallest radius of the beam. So that's why this mirror needs to be curved, so that we have the focal point here. We have the waist here. And the second waist is here inside the active medium, which is the ytterbium doped calcium fluoride crystal or glass. So the let's say take-home message from that is that resonators can be more complicated than just 2 mirrors. Sometimes we need more, but the absolute minimum is of course 2. Sometimes it might also happen that the laser can work even without any mirrors, but this is because there are some parasitic reflections from the gain medium. So for example, this happens often in fiber lasers, when the fiber, the optical fiber, which is the gain medium, so there are ions, for example, of erbium inside the fiber. So the optical fiber is doped with erbium. It has a very large gain. And if we just insert the pump into this laser, so we just pump the fiber, even if we don't place any mirrors, but we just cleave the fiber perpendicularly to the optical axis. So this is the, let's say, image of the fiber. So we have the core and the cladding, and if we just cleave it just perpendicularly, so we have 90 degrees here, such of a surface will provide a feedback of 4% because of the differences between the refractive index of air and of the fiber, because air has the index of 1 and the fiber has the index of 1.45. So we have something like unmatched impedance in electronics, right? So you will have reflections from if you don't have impedance matching. And the same applies to optics. So if the light travels from a large index to a low index, we will see that there is some reflection. So it might happen that if you just have a bare fiber without any mirrors and you will have 4% of reflection from both ends, this is enough for a laser. So we can build a laser which doesn't have any mirrors, physical mirrors, but there is a parasitic mirror because of this 4% of reflection. Okay, so now we will move to another important topic, which is the broadening of laser lines. So you already know that laser can be a single mode, which emits just one emission line, or multi-mode, so it emits many lines. But what about the width of these lines? So generally, we already introduced the on the previous lecture. We had the maybe I'll go back to the first slide, because this was important. So we introduced the empty cavity line here. So we remember that the empty resonator has some resonances spaced by the frequency FSR, and these resonances have their width, which is defined with this formula. And probably I gave you some examples that when the reflectivities of the mirrors are at the level of 97% and 1 meter spacing, the width of the resonance can be at the level of, let's say, 500 kilohertz. Okay. But how does it apply to the width of the line that is emitted by the laser? Okay, because this is what I mean with this 500 kilohertz. This is the line width of the resonance of the resonator. But when we have the gain bandwidth, and then our laser will emit a longitudinal mode, then how is this here transferring to the line width of the emission of the laser? And this is described by the Shawlow-Towns equation. So maybe you remember that Charles Towns and Arthur Shawlow received the Nobel Prize for their contribution to the to lasers. As far as I remember, Shaolo was the brother-in-law of Charles Towns. So they worked together, and they were also family. And they introduced a formula which is now called the Shaolo-Towns equation, here highlighted in red color. And this formula describes the line width of the laser emission, let's say the laser oscillation, at a given output power and at a given empty cavity line width. And this formula takes into account also the spontaneous emission from the atoms inside the laser. So this is described by this Planck constant, and the N0 is the central is the frequency, right, of the laser. So in general, it will happen that if we put like 500 kilohertz here, because this is the result of our empty cavity line width, general, this number will be much smaller than 500 kilohertz, which means that when we turn on the laser line width, here marked as delta Ni Ost, will be much narrower than the line width of the resonator. So the oscillation, the stimulated emission of the laser will just make the emission line narrower than what is resulting from the empty cavity. And here you can see some representative examples of line widths of lasers. It is worth to say that the Shaolo-Towns equation just describes the narrowest possible line, which is the theoretical physical limit. And practically in real life, it's impossible to get even close to this limit because we have many other factors that are disturbing the line width. Okay, but the absolute maximum limit is the Shaolo-Towns equation. So for a helium neon laser, for example, when the output power is 2 milliwatts and we have the empty cavity of 500 kilohertz, the resulting narrowest possible line width is C 10 to minus 4 hertz. So this is like millihertz. So this is a very narrow line. So this is the physical limit. But practically, these lines are at the level of some hertz or kilohertz. So there exists some line broadening mechanisms that are responsible for broadening of the lines from this theoretical limit. And today we will discuss a little bit these limitations and these line broadening mechanisms. So generally we have three reasons of spectral broadening in lasers. Natural, so-called natural broadening, collisional broadening, and Doppler broadening. And I will briefly describe all of these methods, all of these reasons of broadening. The first two of them are also, they are referred to as homogeneous line broadening, and the Doppler broadening is inhomogeneous. So homogeneous, inhomogeneous means that in case of homogeneous, all atoms will react in the same way on this broadening mechanism. And inhomogeneous means that each atom will have its own kind of broadening reaction because of the this mechanism. So let's assume that we have a two-level system. Okay, so we have an atom which has two energy levels, 1 and 2. We have some populations of atoms on these levels, and we have just two energy states. Okay, so the emission will occur from level 2 to level 1, and here we emit the photon with the energy given here. So natural broadening, also called intrinsic broadening, originates from the spontaneous emission of the atoms which are inside our gain medium. So, of course, as we already said, the laser is dominated by stimulated emission, but still we need to consider that there still will be some spontaneous emission. Okay, so if the atom is in the upper state, it can spontaneously decay to the ground state and emit a photon. And this transition will occur, of course, with some probability. So it will occur statistically in the time tau 2-1, which is called the transition lifetime. So we say about transition lifetime, we say that this is the time that is needed for the atom to decay to the ground state after being excited to the state. The atom exists here in this state over some time and then decays to the ground state and emits a photon. So the time that the atom is staying on the upper energy level is called the transition lifetime. Okay, and because of this transition lifetime, because of the fact that some of the atoms, this is just random, right? So since some atoms can stay for a longer or shorter time on this upper level, this will translate into broadening of the spectrum of the photons emitted from this energy level. So we will have a central wavelength, central frequency here, but the distribution of the spectrum of these photons will be described by a function here, g, which will have some width. So these transitions are not monochromatic. So we could say that they have some width. So this is let's say illustrated here, that we have some distribution. So these lines, these atomic levels, they are not ideally discrete lines that generate monochromatic radiation, but they have some width. And this spontaneous emission is given by a Lorentzian spectrum, a Lorentzian function. So we have a central frequency and we have some full width at half maximum. And this is proportional to this lifetime, to this transition lifetime. And in general, the longer the lifetime, the narrower the lines, okay? Because the full width at half maximum of this line, of this naturally broadened line, is defined by this formula. So this is 1/2 pi times the lifetime. So typically, for just typical solid state lasers, for example, the lifetimes of these transitions are at the level of 10 to minus 8. Okay, so this is like there may be some microseconds, sometimes nanoseconds. So if we calculate that, the resulting line widths are at the level of megahertz, so tens of megahertz. But there exist lines that have much longer lifetimes, especially in gas lasers. So in gas lasers, if we have this upper energy state, the lifetime of this state is very long. So when the atom is excited to the state, it will stay there for sometimes even seconds before it will lose its energy. So some of the lines, they might be very, very narrow, sometimes for hertz, at the hertz level. Yeah, so the line width will be at the level of hertz. But usually this depends on the gain medium, but in typical gain media, this will translate into megahertz range. So this is an example for 10 nanoseconds. The natural broadening of the line will be 16 megahertz. So you can see how far it is from the theoretical limits set by the shallow Thorne's equation, right? So it's really far away from that, because it might cause some serious broadening. So this is the first reason, the natural broadening. The other second reason for broadening of laser lines is so-called pressure broadening, or also called collisional broadening. So this can be seen especially in gas lasers. So a gas laser is just a container of some atoms in the gas form. So as you can guess, these atoms move around in this gas mixture, and then they can collide with each other. So these atoms can just bounce together. They can collide with the walls. They collide with also the mirrors. And the collision of two atoms, it will change their wave function. So if you can imagine that an atom will generate a photon, but then another atom will hit this atom, you can observe some kind of a phase jump in the emitted line. Okay, so it should look like that, but we see some phase jump in the emitted radiation from this atom because of this collision. So if there are these phase jumps, you can guess that any phase modulation translates into frequency modulation, right? And these collisions, they just interrupt the process of this interaction between the waves and the atoms, because we still need to have coherent stimulated emissions. So we have photons incoming from this side, right? And these atoms, they need to absorb the photons and generate next photons in the process of stimulated emission. But if they collide together, they will cause the collisions will cause these interruptions in the phase. So due to the phase jumps, the atoms will not see a monochromatic wave anymore. So because of this jump, if we look at the spectrum of this phase, spectrum of this wave, this will not be a Dirac function anymore, right? Because of this phase jump. And the measure of this collisional broadening is the collisional lifetime, which is given by this formula. So we have the gas density. We can define the effective frequency of the collisions, collision cross-section of an atom. So this is just kind of a measure of the probability of collisions, and the average velocity of the atom or the molecule. So they these factors contribute to the collisional broadening. And once again, also the collisional broadening is described by a Lorentzian shape. So the laser line that is broadened because of the collisions or just pressure broadening will have a Lorentzian shape. So this is the general formula. So this tau here now is something that combines the collisional lifetime and the just lifetime of the energy state from the natural broadening, right? And if the pressure would be zero, right? So we have no gas, then of course we have only natural broadening. And the line width is described by a very similar formula to the previous one. So we have the collisional broadening 1 over pi times collisional lifetime. So in gas lasers, the collisional lifetime, I've taken this formula from this photo book, can be calculated using this formula. So it takes into account the gas pressure, atomic mass, and also the radius of the atom. So this is a different formula that I showed you before. And as an example for a helium, again for a helium neon laser, if we assume that the pressure inside is half torr, so I don't know if you're familiar with the unit of torr. So torr is 1 over 760 the atmospheric pressure. So generally low pressure. So the pressure in gas lasers is very low. So we can guess why, because we just want to avoid collisions. Okay. So the pressure is half of the torr. The radius of the atom 0.1 nanometer, and the lifetime of the collisional lifetime resulting from this is half of a microsecond. Then we will have the collisional broadening, the line width at the level of less than 1 megahertz. So 0.64 megahertz. So we see that it's much lower than the natural broadening, which was about 16 megahertz. So the conclusion from this collisional broadening is that in any atom, the collisions of the gas will contribute to the broadening of the spectral line. And we can define a broadening coefficient because this is proportional to the pressure of the gas. So that's why we often define a collisional broadening coefficient expressed in megahertz per 1 torr of pressure. So for example, for a Heine laser, this is approximately 70 megahertz per torr of pressure. And in the CO2 laser, about 5 megahertz per torr. So at atmospheric pressures, if we would, of course, have the atmospheric pressure, the lines would be very broadened because the atmospheric pressure is 760 torrs, right? So this is a very high pressure. So this is also important for spectroscopy when we measure absorption lines in spectroscopy. Then when we measure them in atmospheric pressure, they are really, really broad at the level of gigahertz. But if we want to build a laser and we want to have as narrow lines as possible, then we need to lower the pressure of the gas to minimize the probability of collisions. But on the other hand, we cannot minimize the pressure of the gas until zero pressure because we will have no atoms to emit photons, right? But this is always a trade-off. So that's why it took so long the guys to invent the gas laser, because Ali Javan was working on the gas laser and in the 50s, and he managed to achieve the first emission in the late 60s, months after the first laser done by Theodor Maiman, which was the Ruby laser. because in ruby laser we have much less parameters. Like in gas lasers, we have the pressure of the gas, the mixture, the ratio, and so on and so on. So the conclusion from that is that in gas lasers we will have collisional broadening, and the higher the pressure, then the more broadening we have, and you can define the broadening coefficient, and that's why you have low pressure in the gas lasers. And the third mechanism of line broadening is the Doppler broadening. So Doppler broadening is dominant in lasers which have low pressures. So when we don't have too much collisional broadening. So in the case we want to avoid collisional broadening, then Christian Doppler appears and introduces his Doppler broadening. So what is the principle of that? So the principle is that you're aware of the Doppler effect. So when some object that is emitting waves is moving with respect to the observer, the observer will observe a changed frequency, right? And the same applies to the photons emitted from atoms. So you can see it here on this illustration. So this is the observer here. This is the eye, and we observe that the atoms emit photons, but the atoms are moving. So even if they emit the photons in the same direction, because this is stimulated emission, so the photons have the same phase in the same direction, but the atom is moving. So if the atom is moving, for example, this direction, then I will see a change in the frequency of the light emitted from this atom, right? So if every atom or molecule is moving with respect to the observer, we will observe a gigantic shift in all these frequencies. So this will be a huge mixture of many frequencies. Of course, luckily, this is not a very visible effect. I mean, it still broadens the line, but in some limited way, right? So the impact on the entire line width is limited, but we will see a distribution of frequencies, and the width of this distribution will be proportional to the velocity distribution of the atoms. So the frequency of the photon will be changed by this Doppler coefficient. So the nu z is the positive or negative velocity component depending on the direction of the atom. So if the atom moves in one direction, we have plus, or in the other direction away from the observer, we have the minus. And the velocity distribution here in the gas medium is described by a Gaussian shape. Okay. So we define something which is called the most probable velocity and some velocity distribution in the frequency domain. But maybe I will skip these ugly formulas for you. But the most important thing here is that the line shape determined by the Doppler effect is Gaussian, and the spectral width of the line is described by this formula. So this function is the line shape, right? So this is the shape of this line, and this here is the so this is the function, and this is the calculation of the width. So you can see what does it take into account. So we have the of course the temperature, but also the contribution of this factor here, which is related on one slide back here. This is the most probable velocity and also the atomic mass in the gas medium. Yeah, and this here is the, let's say, simplified version of the same. So if we now summarize the impact of the Doppler natural and pressure broadening on the gas laser, you can see that in the helium neon laser, for example, the Doppler shift might have the most dominant influence on the line shape, even up to gigahertz. Because in real life, we don't see such broadenings because if we stabilize the temperature and we have the let's say thermal equilibrium, then we somehow minimize this Doppler shift, but it might even reach gigahertz. The pressure broadening is much lower, so it contributes by less than 1 megahertz, and the natural about few megahertz. So this table summarizes also some Doppler broadening and collisional broadening line widths for helium neon and CO2 laser. So you already see here what is the difference between the line width of a CO2 laser, which is at the low pressure of 10 torr. It's at the level of 60 megahertz. But if the pressure is increased 1 bar, I cannot recalculate bar to torrs right now, but you can guess that 1 bar is much higher. So you have 40 gigahertz. So increasing the pressure of the laser of the gas inside the medium will significantly increase the line width. So the depending on the conditions, we will have always a mixture of these three effects, right? So we can define just kind of an integral that will combine the line shape, the shape of the spectral line, which is a convolution of the Doppler broadening and the Lorentzian function from the collisional broadening. Okay. And each of these collisional mechanisms will contribute in its own way. But the conclusion from that is that we have these three effects, and as I said at the beginning, the Doppler broadening is inhomogeneous. Why is it inhomogeneous? Because each atom has its own velocity and its own direction, right? So if they emit the photons in the same direction, but they move around in different directions, then the Doppler broadening will cause so-called inhomogeneous broadening, because each atom will emit a photon with a different frequency. So this Doppler broadening does not interact in the same way with all atoms of the gain medium, right? In case of collisional broadening, we can assume that if we increase the pressure, then we will just increase the probability of collisions of all atoms. So we cannot just predict that some of the atoms will avoid collisions, right? And the same applies to natural broadening, since this is just completely random and resulting from just spontaneous emission. This is homogeneous, so all atoms will act in the same way, right? But Doppler broadening is inhomogeneous, so every atom will react in a different way, because each atom can move with a different velocity or a different direction. So it's good to have an impression also about the contribution of all these effects on the line width. So the Doppler is the most contributing to the line width. Then the natural broadening and the pressure broadening has the less impact because we use low pressures. But please remember that if we increase the pressure, we increase the pressure broadening. Do you have any questions regarding the broadening mechanism? Okay, if not, then I will just move to the generally my last slide today, because I didn't mention probably yet about the energy level signature of atoms that are used in laser media. So far we always considered this kind of situation where we have a two-level system, right? So we have a ground state and the upper state, and we assume that our photons are emitted from the state 2 and the atom decays to state 1 and emits a photon. However, it's generally it's impossible to obtain laser emission from this kind of system. So this kind of system cannot be used in lasers. This is because just the reason that in this kind of system we have the same energy gap for the absorption and for the emission. So when the incoming photon will come from this side, then we could have some kind of a collision, because some atoms would like to absorb this incoming photon and just have absorption. But on the other hand, the excited photons would like to, the excited atoms would like to use this photon to induce stimulated emission. So in this case, this kind of system could not work. So in lasers, we use atoms, atomic systems, or molecular systems. So we just use media that have a 3-level or a 4-level system. So a 3-level system works like that. So we have the ground state, and we pump our laser medium. So we deliver energy. So this might be either current in the semiconductor, a discharge in the gas, or optical pumping in fiber or semiconductor lasers. So we excite our atoms to the upper energy level, and after some time we will have a non-radiative decay. So this is the non-radiative transition decay. So the atom from this level will just lose its energy, but without emitting a photon. So this is also possible. The atom doesn't have to emit photons every time. So it might just lose its energy because some also, for example, collisions or some interactions between two atoms. It can just lose its energy without emitting a photon and just moving into a lower energy level, to the level 2. And now from this level, the atom emits a photon. So it decays to the ground state, and we have a radiative transition. So this is the laser beam the laser beam will be if we will have also the feedback. So we will have photons from incoming photons, and we have the stimulated emission here. So the absorption occurs between the level 1 and 3. So this is the absorption. And the emission occurs between levels 2 and 1. So we have two different transitions used for absorption and emission. Okay, and you can see that the energy gap is bigger for the absorption, right? So if we consider optical pumping, we need to deliver more energy, so a shorter wavelength than the emitted from the laser. So as an example of a 3-level system, you could say this would be a ruby laser. So the world's first laser was the ruby laser. And the absorption wavelength is around, I don't remember exactly, but let's say 450 nanometers. And the emission occurs at around 600, let's say, 600 nanometers. So the red wavelength. So you see that the wavelength here is shorter because the energy is lower. So the band gap here is smaller. Okay, and in case of a full level system, we have the absorption to the third state. So we have the atom here on the upper state. Then we again have a non-radiative transfer to the second state. And here the emission of the photon occurs when there is a transition of the atom from level 2 to 1. So we have the photon. And then the atom is still not on the ground state, but on the first state, which is a little bit up from the ground state. And here we have to use this relaxation to the ground state. So again, we have a decay, non-radiative decay. This might be also caused by, for example, collision with the walls. So the atom just collides with the wall of the laser tube, of the container, and loses its energy and decays to the ground state. So maybe you have a guess which system, 3 or 4 level, is more efficient, is preferred, which one is better, which one is worse. Maybe someone has an idea.
3 level is more energy for the photons?
Yeah, so 3 level, it's not the correct answer. So the 4 level system is better. It's much better. Why? Because we need to remember that we need to have population inversion, right? To have a laser. So if we need population inversion, which means that we need to have more atoms on the upper energy state and less, more than on the ground state, right? So in a 3-level system, the laser transition, the emission of the photons, occurs between the state 2, the upper state. Maybe I will remove this handwriting if you don't mind. Maybe it will be easier. So the in a 3-level, the laser emission occurs between state 2 and the ground state. So to obtain population inversion, we need to have a lot of atoms here on this state. Why? Because in thermal equilibrium, or in general, we will always have some population on the ground state because of Boltzmann distribution. So the ground state, you can assume that the ground state is always occupied by some atoms. So let's assume that I have 7 atoms on the ground state. So to obtain population inversion, I need to have 8 atoms, at least 8 atoms on the second energy level, right? So I need to pump a lot to have this population inversion. In the 4-level system, the laser emission, the emission of the coherent photons, occurs between the state 2 and state 1. And the state 1 is not the ground state, so it lies above the ground state. So I have a lot of atoms on the ground state, but I don't care about the population of the ground state, because I just care about the difference between the population on the end of the level 2 and 1. And in general, in 4-level systems, we can assume that the level 1 is always almost empty, because the lifetime of this level here is really short. So it's get depopulated very fast. So even if I have like billions of atoms on the ground state, I just need to have 1 atom here, or maybe 2 atoms. And I already have population inversion between levels 2 and 1. So I need to have population inversion only between these 2 levels, and I don't care about the population of the ground state. So this is way more efficient in case of lasers. Because as I said, the lifetime of the level 1 is very short, so it gets depopulated very fast. So these atoms just decay very quickly to the ground state. So that's why if we want to build a laser, we usually we use a 4-level medium. So a 4-level medium, for example, an erbium or maybe ytterbium ions, ytterbium 3+ ions, we pump them with 976 nanometer wavelength, and the laser emission is at the level of 1064 nanometers. So we have some non-radiative decay here, and then some non-radiative decay here. And the ytterbium lasers, they can achieve the efficiency of over 80%. So they are quite efficient, also because of this 4-level structure. So you don't need so much energy for pumping of this system to excite the atoms, because you just need to have population inversion between the level 1 and 2. But in the 3-level system, you need to always care about the population of your ground state, because you need to have more atoms on the level 2 than on the ground state. So this is the principle. So in general, in lasers, we use 4-level systems, but there exists, of course, 3-level systems as well. As I said, the Ruby laser, for example, is a 3-level system. But now most of the lasers are 4-level systems. Okay, do you have any questions? Okay, if there are no questions, I have one question. So one announcement. So the next lecture will be, I'm on a conference next week, so I will record a video and upload it on the ePortal. So you can watch it and listen to it. And we will meet in 2 weeks. And my second question is, I just wanted to ask if Miss Julia Rzepka is here, because I would like to talk to you for like maybe 2 minutes after the lecture, if you don't mind. Okay, so there are no questions, then thank you very much. And see you in 2 weeks. Bye-bye.
Thank you. Goodbye.